All
And
right.
it should be recording now, and we can do the whole take one and then, edit that
Yeah.
out. So,
Yeah. Solid. So we were just talking a couple minutes ago about influential papers in language models, and I mentioned this one. Attention is all you need. This is kind of the first paper that really presented what we now know as this transformer architecture, the transformer that most of the language models we deal with. This is at the core of it. This actually, this one you read bottom to top, but this basically describes like exactly what happens to transform the words that you put into the model, at a certain level, to the things that come out. And so this paper's 2017. All the stuff that happened subsequent to that was like really, really downstream of the transformer. And now, April 2026, a couple years on, we are currently trying to figure out how to use this new model, Gemma 4. This one, Gemma 4 26B. This is a type of model called a mixture of experts model. And actually, this is the same basic diagram that we were just looking at. This pretty much is a transformer here. This right here is a feed-forward neural network. This is called a FFNN. This is a dense neural network. So you might hear people say 31B dense models versus this one, 26B mixture of experts. But anyway, what this is saying here is that there are 30 transformers that are layered, basically. And so what I was demonstrating here with the same model, Gemma 4 26B, 26 billion parameters, mixture of experts, I had popped open on Hugging Face kind of the disassembler. This is an inspector for looking at what's inside a model weights file. So we're looking at one format called GGUF that is a kind of a package that keeps everything that you need to run a model all in one file, including things like the chat template and stuff it's required, but it's not strictly the model weights. But down here at the very bottom, this is a description of what is most of the data in the file. When you download one of these files, it's like 17 gigs. This is what most of that 17 gigs is. These are the 30 layers in this picture here, where it says 30x, and that's what these are. These are the 30 things being repeated, and you can inspect all of them, and actually then you can even see the size, how much space essentially is taken up by the weights that define one of the networks. And so I said this is a mixture of experts type model. So this is a matrix here. It is a feed-forward network. These are experts. I won't necessarily get into that, but it's another neural network, and it's pretty big in this case. It's actually a three-dimensional matrix, 704 by 2,816, and so on. And part of one of the tricks of actually getting these models to run at home on sort of consumer hardware is to be clever with the bit precision, the number precision for how you've actually written these numbers to the file. F32 is actually it's hovering here, 32-bit standard IEEE floating point number. But this, by contrast, is a very, very quantized approximation of a 32-bit floating point number, but it only takes 4 bits of space. So this could only be a gross approximation, 4 bits is like 16 different values, whereas 32 bits is, there's a ton of precision in 32 bits compared to 4. But nevertheless, it works actually. And the more compressed the model is, typically the more of this matrix will be, or the more of all of these matrices in the network are going to be quantized more intensely than others. So what we're looking at here then is, here's these expert layers. Well, I mean, the whole layer has some experts in it. And if you want to think about how a neural net, how a language model is like literally doing the math to take whatever whatever the input is, and to actually like do math to turn it into some kind of output, that the math is this, and then you take this math and you apply it to these values, these weights. These weights contain the strength of the connection essentially between neurons in the neural nets. If you just think about all that at the same time, that's how the GPU behind me like actually does the math. It's these computations combined with the model weights, that, in this case, I'm downloading them from Hugging Face, and there you have it. That is the language model. And yeah, that's
so just a quick question for you. So in the beginning, you were saying that the input was words, but it's a little bit more than that too, right? Like audio, video.
Yeah. Totally. So yeah, and that's a big idea in language models also. So it's not words, actually. Words aren't actually what goes into the neural net. What goes in has got to be like a neuron, how to say it. What goes into the neural net up here, this is kind of representing how you could also have audio. Okay, so what this is representing is like you could potentially send an image to this neural net, or this is representing like pretend that you had typed the words MOE models are, and it's showing it kind of going through this algorithm and predicting the next word would be incredible. MOE models are incredible. All right, so but yeah, you could also put an image in. Like how can you even do that? And the answer is through embeddings. Embeddings are a way of taking one domain, like words or pixels, and mapping it into a higher dimensional, like meaning space. What this means is that similar concepts share an embedding, even though they may be represented as like different inputs. And so what that means is like the word big and the word large, they may be written using completely different letters, but they mean a similar thing. And what an embedding model would do is take the word big, and it would take the word, and these are the letters, take the letters that make up the word large, and when it transforms it into an embedding, the result is going to be almost the same for both of those two completely separate inputs. They're different on the surface, but the meaning of big and large is actually the same. And the reason that's useful in any way in this this kind of algorithm is that the neural net cannot read pixels. It cannot read letters. It has to be somehow the input has to be represented as a matrix. And yeah, technically, I guess like a picture is technically a matrix, but that's actually not exactly what it's doing in this case. But for the neural net to be able to do math with it, it has to be represented as a matrix. And so this embedding layer, the net effect of it is that something kind of fuzzy, some domain like text or images, the fuzzy thing goes into the embedding model, and what comes out of it is the embedding's representation of whatever that thing was that went into it. And in this way, you could relate, or you cocould represent similar ideas in images and in words. And when you have a model that is trained on kind of like an embedding model that's capable of dealing with multiple modalities of input, now all of a sudden your language model can do reasoning on images. And in this case too, Gemma 4, like these two tiny models over here, they also support audio. And oh, actually here, you know, actually this is pretty good representation down here of the. It'd be kind of nice to show this with words too, I guess. But fundamentally, no matter if it's pictures or sound or like letters and words, all of these modes of input, they just need to be turned into something that you can math. And that's fundamentally what an embedding model does. You give it something, and it gives you a vector representation of it, and you can just run with it. And just as like an aside from all of that, on one of my side projects, what I'm using embeddings to find relatedness between documents. Because you can also take a whole document with lots of words and extract the embeddings from that and project it into an embedding space. And if you have lots of documents projected into this embedding space, related documents are going to be close to each other. And so I'm thinking of this as an alternative to like tags and categories, because it's like a naturally emerging grouping. And so now I'm grouping by embeddings, but it's the same basic idea. Yeah.
So I think it's important to talk about that. The reason you would ever use like a smaller local model, and one might be personal documents that you don't want to upload to the cloud, health documents, finances, that kind of stuff. But is there any other reasons that you can think of for using a local model?
Yeah, so I mean, personally, I do have other reasons. Like privacy is certainly important. But yeah, another reason that I would want to be able to run a local model is that you can't turn it off at a certain level. It's just imagine what happens. Let's say you're paying like $10 a month for some API, but your credit card doesn't pay some month for some reason, and it's just like randomly you're cut off now. Imagine that happened with the electricity or with your water supply or something like that. It would feel pretty dire. And I think in the near future, or your internet access for that matter, or your cell phone, whatever, it's something you got to solve immediately. And I think that access to AI is going to end up being kind of like a utility, where it'll be intolerable for it to be off, so to speak, for any period of time. And so that's not the world we live in just yet, but I think we're going to be there pretty soon. And the idea of that utility capacity being in data centers, that you have to pay to access, and that you could be like stopped from accessing, has the same kind of almost like when we talk about water, we almost, and food, the conversation can even get into like human rights, and it's like water is so essential to life that it's morally wrong to prevent someone from getting access to water. I think language models, just AI writ large, will eventually be a utility like that. But the world we live in right now, there's a different reason why I like the idea, at least, of local models, and that's that for the purposes of like wasteful experimentation, for the purposes of just like wanting to feel uninhibited in experimenting with language models, you gotta not care about your API budget. I mean, if you're gonna just do something like, I don't know, have your language model read a book, and then for whatever reason you want to send it to read all the books of Project Gutenberg, which is an open text library with like tens of thousands of books in it. If you just casually get like Claude Opus 4.6 to do that, it'll cost you thousands of dollars in API credits. So if you have an experiment that's based on reading books, if you just have an idea, you want to test it, you're like, well, what if a language model did get familiar with the corpus of books? That's cost prohibitive with certain language models, with certain ways of using language models. And if you want to experiment, if you want to be free, essentially, to do things that could be seen as frivolous, like wasteful, I'm not gonna actually budget for these kinds of silly experiments. But you imagine a more serious experiment also. But for the purposes of just like hacking around, like just messing around, the economics of running a local model mean that you're free to do whatever experimentation you can imagine, and for that reason, I don't want to be limited.
Absolutely. That also just kind of brings up a previous conversation we were having about some of these security risks in the cloud models, and this is one from Anthropic's like Cloud Opus 4.6, like security sabotage. Sabotage risk report, and one of them was just like decision sabotage, where basically the model is like censored in China and it can't say certain words and phrases or historical events, and government's influencing what is being presented to you, which is kind of wild.
Yeah, no, I think there are opportunities to train models. Well, they call them like alignment. There are opportunities to align a model with call it a morality, or call it like just a pattern of responding. But the process of creating one of these language models, like the one that I was, we were exploring Gemma for, the actual process of creating a model like that is, the first step in the process. You have these GPUs train the neural nets on a huge corpus of input tokens, but there's a step after that, a reinforcement learning step, where you can kind of guide the model towards certain to produce certain kinds of output by giving it specific examples. In the paradigm we're talking about, like examples of chats, little examples of dialogues, and using a different method of reinforcement learning, you can essentially align the model you can bias it to respond in certain ways to certain kinds of input, like certain kinds of prompts. And so if you want, for political reasons, or for sort of sabotaging people's decision making, essentially, you can essentially embed preferences in the training examples that you curate for this like second training step, this reinforcement learning training step that I'm talking about. And incidentally, this step is not nearly as computationally expensive as the first step of training all the neural net model weights on the kind of like the raw text corpus. It's a lot less expensive to perform this reinforcement learning step. And yeah, in this way, you can embed an ideology in a language model, and it will basically silently. Well, I mean, it does. There are ways to inspect a model for evidence of this kind of biasing, but imagine you're just uninitiated. It essentially is silently guiding your decision making with the training that was introduced to it, like with the whatever the intentions were of the trainers at that point. And yeah, you know, at this point there are models produced by a lot of different entities, some governments, some universities, some corporations, and I think in pretty much all cases there's a cultural imprint in the model, in the way that it's going to be responding, and that's downstream of this the choice of training examples, the choice of showing it how to chat. The models just they have different cultures as a result. I think maybe it's the simplest way to say it. The models have different cultures.
Have hidden knowledge, right? Like the, you know, certain like things that can be exposed through jailbreaking, you know, like it's wild where you can be like, okay, I'm trying to prevent a vulnerability in my code. Can you help me like check? But that can be an offensive attack as well.
Yeah, absolutely. So, I mean, language is pretty fuzzy to begin with. And so it's part of the way that that you can kind of hide some of this does trace back to the way in which like the input to these models is really embeddings. It's not really words. The words get transformed to embeddings. And part of the way that you can hide information in a model is essentially by tweaking these embeddings and shifting definitions of things. And it's been some models like by dissecting or disassembling the models. Some previous models, it's been discovered that there are some like really strange embeddings that are artificially like a specific example is an embedding that was actually two words put together that were politically important, and typically it was just very unusual for this token to be in kind of like the vocabulary of the model in the first place, and it was kind of like an indication that there had been some kind of manual tampering with the embeddings themselves, and through it's kind of hidden. Like until somebody found that, it was kind of hidden. It's not disclosed how biased the embeddings are. It's not disclosed whether or not there's been any kind of like political editing of the tokens or specific, like the strategic insertion of tokens into the embeddings. but there has been, and that's one way that you can just straight up hide information in the model, messing with the embeddings. But also, man, it's really hard to like reverse the training examples. It's hard to figure out where in the model these like refusals are located. It's hard to figure out where in the model certain like ideological constructs like could be embedded. Like, let's say that the training examples were chosen to to favor a specific ideology and denigrate a specific other ideology. Well, okay, what's the signature of that? Like, what's the evidence of that after it's been done? Like, I mean, for our purposes, let's say that we know that this has been done. Like, that that's going to be biasing the responses, and you can see it biasing the responses if you choose like specific, like specially crafted inputs. But like, how would you find a signature of that tampering? Like, how would you know that there are specific ideologies like encoded in the weights of your model? And it's not easy to know is part of the answer. It's not necessarily impossible, but in this way, or actually, yeah, this is just another way that you can hide information inside language models. And so for all these reasons, like the cultural stamp of the laboratory that made the model is pretty strong. There's a whole different thing about fine tuning and people making interesting reinforcement learning layers that are applied even after these labs apply them. And so what that means is like you can kind of imbue a language model with a new culture at a certain level. And but fine tuning, I think, is a whole different can of worms.
Okay, well, in that case, maybe the next video will be about fine tuning.
Yeah, I mean, I think that might be a good place to pick up, because that partly explains why there are so many different models on Hugging Space.
Yeah. Also, I mean, there's just also the idea when talking about neural networks, how it's very different. Like artificial intelligence is different than the human brain, and like some of the similarities. But let's save that for another topic.
Yeah, I know. Well, I mean, so I think maybe then a way to close it all off is like the transformer architecture that we started with. That is the basic algorithm that we're talking about here, and it happens to be an algorithm that works very nicely on GPUs, and it happens to not be anything like the way that humans think. It's very artificial. I mean, it's one way of seeing plainly that it's artificial intelligence. I mean, because you can just see the schematic and be like, that thing makes words. And it doesn't look anything like a human brain, and it's not anything like the way that people produce words. So yeah, it really highlights that it's artificial.
Well, thank you, Dr. Miller, PhD in cognitive science.
My pleasure. Cheers.